Hello? Oh, OK, nice. This is working. So hello, everyone. My short name is Slava, and I'm working in Amazon Web Services deep learning team. And while everyone coming, I just want to mention there is only one short link over there on the main slide. This link basically points to a repository that has all the small examples that I'm going to show today during the presentation itself. So if you do want, you can open it right now and download some of the files or the whole Git repo and follow with me along the way. And while some of you might be doing this and people still coming, I will give you some brief introduction for my presentation. Where I came from, we have this telling that you cannot learn everything, but if you can pick one topic, you can learn it really well. And for the sake of today's presentation, we're going to cover one specific topic of distributed learning. More precise is how to set up a cluster of MXNet and how to actually start training itself. Also, I've been told that I have this Ukrainian accent that time to time hard to decipher, and also it sounds a little bit offensive, even if I'm trying to say something nice. So please don't be tricked by my accent, and if I'm saying something hard that is hard to decipher, interrupt me, but you need to say something. I really can see you guys, so just not only raise your hand, you literally need to say something like, hello, Slava, please repeat something, and I will be more than happy to do it. Okay, so I would assume that everyone who wanted to download the data from the link have done so. So let's start the actual presentation with answering on the one question: why to actually distribute? And I'm going to show you this simple and small image. It's from official Apache MXNet repository that basically shows on the x-axis how many GPUs you're using to train your model. And on the y-axis, it shows how much speed you actually gain with this amount of GPUs. I wouldn't say that it's actually that linear. You will have a lot of bottlenecks, but it gives you some intuition. The more GPUs you're adding, more speed you're gaining. And by the way, for the sake of this presentation, I assume that you guys have some experience with training neural network on your local machine. OK. Before we're going further, let's talk about two main definitions. It's multi-machine, also known as distributed training, and multi-GPU training. And the thing is, good deep learning framework is like Android. You know, Android tries to eat all your batteries on the phone, and the good deep learning frameworks try to eat all your GPUs on the machine. So if you're running local training on one machine, for the sake of this presentation, let's say you're running P2 x 16x large, the EC2 type of instance that has 16K80 GPUs. If you're running local training, you're already doing multi-GPU training because essentially your deep learning framework probably consumes all of them. This means that if you're running non-distribute, one machine local, but multi-GPU training, it puts you on this graph somewhere right here. So you're already doing something that more than zero. And effectively, you have this unreachable dawn with one machine. And this actually might be absolutely OK. And I'm speaking about not this type of OK. I mean, it's really OK. What I've been telling to my students, that distributed training is like a concurrent programming. If you can do your task without, do it without. Don't try to do distributed if you still have a potential of vertical scaling. If you don't have enough power of P2 16x large, try P3 8x large with Volta machines in it. Who knows, might be 8 Volta GPUs could be enough for your speed. And only when you're absolutely sure that you have reached a bottleneck and you do need to do it distributed, only then actually move forward. OK. So what you basically need to have if you want to do distributed training is spin up many machines, ideally with the same configuration, and somehow magically connect all of them in one MXNet cluster that will behave as one logical entity. And we're going to speak how to do this. Okay, so this basically will put you somewhere here. Each particular line is one additional machine, so you can at least have some intuition what speed you will gain when you're setting up the cluster. The key advice here would be to start the cluster with just 2 machines to figure out how to do the cluster, and then incrementally adding more and more computational power. For the sake of this presentation, we will have a really, really small training example. Small training example is just a simple line of the data, and we're going to train our linear regression with MXNet to actually find this function f. So this is like a super simple function, and I choose deliberately such a simple equation so the complexity of our function not going to stand in the way of understanding how we're going to do it distributed. And if you're going to plot this function, obviously it's something like this. Okay, now actual training. Actual training, I literally copy-pasted this from the official MXNet tutorial. I've done this deliberately to show how easy this training, that actually local training, to make a distributed training. We just need to look, oh man, okay, look here, learning rate. It's deliberately small, so it will take a long time. So we will do have some benefits in making it distribute, and KV store. KV store is actually an interesting thing in MXNet. It's something that you need to know really well if you're going to distribute. Essentially, if you're distributing your model, you need to store your model somewhere. If you have more than one machine, you can no longer store this data inside of the memory of the machine. Key value store stands from key value storage, and if you're putting a device, this basically means that your model will be stored on the local device inside of your local memory. Also, key value storage is something that little bit confusing because in different sources it has a different naming. At some point, it has name PS, also stands as parameter server. If you actually go to GitHub and will try to look at source code of this project, it calls PS Lite. If you're going to look inside of the MXNet MAME repository, time to time you will see a name server. And time to time it has name KV store. But all these definitions that I just mentioned, they actually means almost the same. Okay. Now, let's actually distribute this example, simple linear regression training. And before we're going to make it distributed, we need to understand 2 types of distributed training. First one is data parallelism. Second one is model parallelism. It's 2 most popular types of train your model in distributed way. Let's say you have a graph, like a simple neural network that you want to train distributed way. And let's say you have a 2 machine, like very simple example. You have a 2 worker that you need to use in order to train your neural network. Model parallelism will look somewhere like this when you have half of the graph on one of the worker and another half graph of another worker. And they training, each of the worker training only their half of the graph. It's like a very naive, intuitive way of describe model parallelism. While data parallelism basically means that each of the worker has the whole graph itself, and during the training, it's basically sending some updates. Usually, it's your step for your model to some key value storage. Here is our key value storage: dash server, dash parameter server, dash PS Lite. Here's a guy with this green box. Okay. So now let's speak about particularly MXNet and how MXNet doing stuff. First of all, MXNet support only data parallelism. You cannot do model parallelism, unfortunately. Yes. And to do distributed training, MXNet has 3 main logical components that are part of the MX cluster. First one is scheduler. Scheduler is basically a logical entity that is in charge to spin up the cluster itself and making sure that the cluster is capable for start doing the training. This is very important because people who usually used to work with big data, especially with some projects like Kubernetes, they usually think about scheduler or managers as some kind of entity that schedules the work within the cluster. Because like in Kubernetes, you come to the Kubernetes, you're saying, okay, I have this job, please schedule this job to the machine that has enough resources, so many machines. While at MXNet, the whole cluster serves only one purpose, train one particular model. Therefore, scheduler itself doesn't schedule the actual job. The main responsibility of scheduler is set up the cluster and start the training. That's it. And we will see later on the implication of this philosophy. Second logical part is workers. Workers can be many, at least one, but if you're really doing distributed, probably you want at least two, though you can have a configuration with one worker. It's actually the worker that has inside the whole model, doing the training, and sending updates to, and here we come to the third item in the cluster, to the servers. Servers is actual KV store, PS Lite, parameter servers, so on, and the main function of the server to store the whole model itself. If your model is really huge, you can have more than one server, though usually in simple cases, one is more than enough. Okay, now let's see how one can start any of these logical components. If you want to do it distributed and you want to do it today, here is how one can start any logical component of the cluster. Basically, when you're importing MXNet and Python, MXNet will check environmental variables, and if you have set up correctly environmental variables, it will do all the work to spin up a particular logical entity. What MXNet is searching for, first of all, is the role. It might be scheduler, worker, or server. Second is IP address of the scheduler. This part is important. It doesn't matter what the role that you're trying to start, either worker, server, or scheduler, this IP address always IP address of the scheduler. Because when your worker woke up, he needs to know where the scheduler in the network to go to the scheduler and say, hello, scheduler, I'm worker, I'm actually up, could you please add me to the cluster? The same goes to the port. This is always port of the scheduler, even if you're starting the worker, because worker need to know to which port of the scheduler to go and tell him that here I am, I'm worker, I want to be added to the cluster. Next, each of the logical entity need to know about the configuration of the cluster. To be precise, it need to know amount of the servers and amount of the workers in the cluster. This is kind of important. Right now, MXNet has a really simple mechanism of figuring out if you have more than one server, to which particular server to send the model update. And this really simple mechanic basically is a hash based on the amount of the servers. Therefore, worker need to know upfront amount of the servers to figure out which of the servers send which particular part of the model. And the last one, which is really important, is PC verbose. It's just the debug information. By default, when you're going to run it on your production, you will use 0. But when you're going to run your first cluster, like today, we're going to use number 2 with maximum amount of debugging information to see what is going on underneath and has a really good understanding of what's actually going on there. Okay, we're going to spin up this particular test cluster and with one worker, one scheduler, one server, and we're going to do it on one physical machine. At this point, if any of you guys have actually downloaded the GitHub repo, you can go to example cluster and do everything that I'm going to do with us just to see that it's working on your machine. There are 3 files: start scheduler, start server, start worker. And this is the way how you need to execute it. Start scheduler is simple. It's just a schedule. We already discussed what each of these stuff actually means. It has logical type scheduler, port, IP address, and information about the cluster. This is the server. Absolutely the same, except role is server here. Everything else is the same. So Scheduler and server is simple. We just started these two logical entities, now the actual worker. Source code inside of the worker, again, it's just a copy-paste from the linear regression tutorial, just to show the simplicity, with only two changes. These two lines are different from the official tutorial, because official tutorial is local. And with this particular slide, I want to emphasize how simple it is to change your local training to distributed training. Basically, what I'm saying here, okay, I'm worker, and now I'm creating KV store. KV store is just an API, an object that knows how to send data about my model updates to the remote server. And then I'm passing this KV store as an input argument to method feed. That's it. Before, method feed used to have a string device, which means store your model locally. Now you're basically saying, send your model updates to the server. And literally, that's how simple it is. When you're going to start this, you will see all this bunch of the logs that we need to dive deeper, because when you're starting your cluster for the first time, something will go wrong. It's like, it's must, otherwise you're doing it wrong. In order to figure out what exactly wrong, you need to be able to decipher all this information on the slide. Now, okay, in this slide, I will put logs that you will see in your terminal, and the small label with the color. I actually cannot see this label on my screen. Okay, that one, green one. Green label. Green label says on which logical instance these logs is observed. The thing is, when you're going to run it in real life, you will have a lot of machines, and logs not going to be in one place. Right now, when we're running anything in one machine, all the logs in one place, which is not the case in real life. So what's happened at first? First, server, it actually could be worker, saying, okay, hello, scheduler. I am the server. I woke up. My rank is question mark. Please add me to the cluster. Rank is basically unique number that the scheduler is going to assign to each member of the cluster. And it's logically that because the scheduler never saw the server, rank is unknown. Then you will see the confirmation from the server. Essentially, just a confirmation. I am confirming that I got this message. In this message, you can see the beginning question mark, then arrow 1. This basically means that the server received the message from unknown to 1, and just the same message. Usually, the first things to see to check if you have a confirmation on the scheduler side, that the scheduler received everything correctly, that there is no problem of deserialization. We're using protobuf to serialize messages between them. This is like the first check that you need to do if something went wrong, if the network connection is okay. Second, you will see the same in the schedule, worker. Worker is up. He also will go to the scheduler. He also is going to request, please, scheduler, add me to this cluster. Now, when the scheduler have received all the information from the server and from the worker, he actually going to start assigning the ranks. This is important. The scheduler will do any work only when all members of the cluster actually requested to be added to the cluster. Therefore, if you have two workers and the second worker still have not announced himself, the scheduler is not going to do anything. In this particular example, scheduler assigning rank 8 to the server, okay, and server assigning rank 9 to the worker, and sending a confirmation. Hey, worker, you are now part of the cluster with rank 9. In this particular moment, in the protobuf message, you can see that the scheduler sending back to the worker or information about other members in the cluster, like IP addresses, ports of the servers, and all other stuff that the worker need to know for further training. The same essentially goes to the server. It's basically saying, server, now you have rank 8, and now basically you are part of the cluster. At this particular moment, scheduler is happy. He's announcing, I'm connected to one worker, one server. From this moment, we have satisfied the scheduler. Now, the same goes to server. Server acknowledge, now I'm connected to both, to one scheduler, one worker. And the last one is worker. From this very moment, we actually have reached the state when the cluster ready to start training. At this moment, the cluster reached so-called barrier. Barrier is the moment in the cluster where everyone have reached the same state. Whenever each logical entity reaches the barrier, it says to the scheduler, hello, I actually just reached a barrier. Please tell me when everyone else is also at this barrier, and only then I will continue to do my work. Scheduler will calculate how many nodes reach the barrier, and only when everyone ready for to do the training, so everyone reached the first barrier, the scheduler is going to announce, okay, now you worker and you server are free to go, you guys are on your own, and now you actually can do and start do the training. The interesting part happens next. As I mentioned, scheduler not going to schedule any work. It's just responsible for setting up the cluster. Therefore, the work of the scheduler is done. Even though the training just about to begin, the work of the scheduler is done. So the scheduler immediately reached the second barrier. And second barrier, actually the barrier that's going to be reached only when all the training is finished. So literally the scheduler going to sleep all the way during all the training. By knowing this, now I hope you do have understanding that it's not reasonably to allocate the whole machine for the scheduler and put 60 GPU machines just for the scheduler that's going to sleep during the training. And I saw people actually doing this for some reasons. Okay. We're actually going to skip the third lab. It's a lab that has more than one worker. But when you're doing more than one worker, you need to be careful with KV-store modes. Just to keep in mind that KV-store can work in two modes, dist async and dist sync, basically synchronized and asynchronized. And the difference of all, if you have a dist async, second one here, this basically means that the worker is going to send update to the server and immediately continue the training. If you have dist sync, each worker is going to send update to the server and then wait until everyone else in the cluster also have sent the updates to the server. Okay, here are some base misconceptions that are really dangerous when you're doing distributed training, and now I hope you will have some understanding why. Here is actually one of the questions of the Stack Overflow, and I saw a lot of questions like this yes, in my day-to-day work. So I will give you just a moment to read it. So, okay, what basically does it mean? That by adding more machines, the training slows down. And this is common thing. Let me tell you why. Again, if you're coming from the big data world, especially from distributed system like Kubernetes, you might have the understanding that the MXNet cluster works like this. The user comes to the scheduler and say, hey, I want to train my model A with data X. And then somehow, magically, the scheduler going to distribute this data among all the workers. Like here, you worker A, you're training the first half. Here, worker B, you're training the second half. Here, worker 3, you're training the third half. But in reality, as I said, MXNet is not a general purpose cluster. Cluster of MXNet always started for one particular model. Therefore, in reality, it looks like this. You, as a developer, supposed to write the source code that knows how to split the data between the workers. And the most common mistake that I saw when the people somehow sharing the file system across all the workers, yes, they shuffling the data on the file system, then they sharing this file system across all the workers, and then start the training, which basically means that each of the worker will do the training with absolutely same sequence, with the same data, and will send absolutely same updates to the servers. It's essentially like having one worker, but then multiply your update on 2 or 3 or 4 or whatever you actually want. So it's like, yeah, shooting yourself in the leg. Now, when you have a good understanding of what you need to do, and you have a good understanding what is KV-store and how to start distributed training, essentially you just need to pass a KV-store in the method fit when you're starting a worker, you can find that KV-store are literally everywhere. Here is random example of LSTM that I just took from, again, official web page, you will see KV store is an input argument. And if you're working with MXNet, you will see that it's really simple because feed has itself input arguments of KV store. So all the examples that you can find already ready for distributed training. You just need to spin up a KV store, spin up a cluster. That's it. It's really that simple. You need to keep in mind about data separation, though. We also have a file launchpy. It's literally just a file that has some helper functionality. You can provide number of workers that you want, number of servers, and the file with IP addresses of SSHable machine. And this file essentially going to SSH the machine, going to spin up the workers or the servers, and do all this dirty work for you. But you need to be really, really careful. Majority of the problem that I just described happens with the users who ignoring all this part about understanding how the cluster works and just using launchpy. And launchpy itself cannot prevent you from training on the same data that I just described. Main slide. Yes, thank you. I think I'm even slightly earlier than I thought. Okay, so a lot of stuff still remains untold here because it's hard to squeeze everything in half an hour. For instance, how the worker pull the data. The thing is, when the worker communicates with the server, the worker always need to know that it's training accurate models. So whenever he pulls data to train on the GPU, worker has a special scheduler inside that knows how to pull updated models from the servers. So whenever the data on the GPU is done, and trained, he already have an updated chunk of the model or the graph to upload to the GPU and continue training. But it will require half an hour more. So thank you. If anyone have any questions, I would be more than happy to answer them. Thanks. Yes. So the question, if you have two workers and they uploading data to the server, if you do any average across the workers. And the short answer is no, because you can have asynchronous mechanism. Basically, workers just fire the updates. And in fact, you can have more than one update from worker one, while you still have 0 update from worker two in asynchronous. So there is no actually effective way to do this. When you're doing a multi-GPU, inside of multi-GPU, yes, you can average everything from your GPUs before actually sending to the service itself. But when you're speaking about multi-machine, no, there is no such thing, mostly because, as I said, you can have non-heterogeneous machines. One is way more powerful than another, and for some reason, you still want to use this configuration. So, no, there will be no average. Just update for your model, just a gradient step if you want. And the PS parameter server just knows how to apply this gradient step. This is actually the reason why we have not reused existing key value storage on the market and implemented PS Lite, mostly because PS Lite just know how to do some stuff that we need, like apply gradients for the model and stuff like this. That plain key value store has no idea how to do. I hope this answered. Yeah. Okay, this is a good question, how they combine information. The thing is, and this is key part, that each worker trains on a different data. You need either to shuffle them, so basically, let's say you want to recognize two objects on the image. One worker can try to train on object A, another worker on object B. So technically, they will sending a gradients updates for different aspects of the model. Essentially, you can think about this as you have one worker, and this one worker trains first on the first chunk of data, then on the second chunk of data. It will be almost the same. I'm saying almost because, yes, in each particular moment, each of the worker will have slightly outdated version of the model. This is true. but still, it's almost the same as you will have one worker string. And also keep in mind that workers pull updated model. So yes. Any other questions? Okay, I think I have 10 seconds left. Ha. Thank you.